Thank you. Thank you very much. I am Charles Twardy. I'm currently a senior data scientist with KeyW Corporation. We are a government contractor in the DC area. I'd like to thank Stefan for inviting me because I'm giving you a talk where I did not use Bayesian. And to my company, this is work that I did before I joined them, though as you'll see at the end, we're hoping to begin a project early in 2019 that builds on this. My task is to entertain you for the next 15-20 minutes before lunch, and because you are a wonderfully weird crowd, you consider BayesNets to be entertaining. I shall endeavor not to disappoint you. I was not always a data scientist. I was a philosopher and a cognitive scientist finishing my PhD in 1999 on causation. I was interested in how people learned causation, how we represent and reason with it, and in that last year of my dissertation, I heard 2 talks on BayesNets and went to my outside advisor because I would be too embarrassed to go to my inside advisor. Said, "Sensei, what do I do? This is so far ahead of everything I've been working with." He said, "Don't worry, finish your dissertation, it's fine as it is. Apply for a postdoc to go work with one of these people to continue your training." And so one of them was from Pittsburgh and one was from Melbourne, Australia. I applied to go work with Kevin Korb in Melbourne, Australia, and spent a wonderful 5 years there learning BayesNets for causation, but I accidentally picked up some marketable skills in data analysis. And that eventually, in a roundabout way, led me to where I am now. In addition to thanking KeyW and Bayesian for letting me be here today, I really need to thank the team that did the work that I'm going to talk to you about. I was at George Mason University at the time, working with a number of wonderful companies, including, let me highlight in the top right here, Cultivate Labs, based right here in Chicago. If you have crowdfunding or crowdsourced forecasting work, I highly recommend you give them a call. They're fantastic to work with. They built our interface and did all of the crowd wrangling for us on the crowdsource project I'm about to tell you about. We were funded by IARPA, the Intelligence Advanced Research Project Activity. So they do fund really cool things, like working on metamaterials, which eventually someday, possibly in an alternate world, could lead to invisibility cloaks. Right now, you can hide very, very small objects of one wavelength. And they fund analysis work, which is fantastic for ex-philosophers like myself who are trying to improve the way people think. They ran a 4-year forecasting tournament on geopolitical events. Hopefully you've heard about it, the book Super Forecasting by Phil Tetlock, the #1 team. Absolutely fantastic work. We were the #2 team. We did very well. We passed all the thresholds. Tetlock's team was just amazing. Kudos to a super well-designed experiment and really good analysis for how to pick out and weight the proper forecasters. We used a prediction market approach. And a new kind of prediction market. So I'm not going to dive too deep into what prediction markets are. Going to start with why should you be interested in them at all? They do work very well for forecasting lots of different things. So here's a result that came out of our science and tech forecasting. After 2 years, they asked us to move to science and tech forecasting because they thought it would be a better fit for the alien technology we were developing. And because the Good Judgment team was clearly handling the mail on the geopolitical forecasting. Question, how many states will report at least one case of West Nile virus, a particular strain of it, the human neuroinvasive strain, by August 1st? The question went live on July 1st. It was a multi-state question, so 0 to 15 states. You know, I'll say states because you're all BayesNet folks and you're used to thinking in those terms. It looked like a prediction market to the people who liked our prediction market interface, and it looked like kind of a web interface to a BayesNet to those who like surveys or BayesNets. The market started out pretty close to what ended up being the right answer. It went down a little bit as people digested early news and adjusted things, went back up, and then within a couple weeks settled down to within ±1 of the correct answer. So that was pretty good lead time. We were happy with that result. Not all our results were that good. Obviously, I picked which one goes on this slide, but as you'll see on the whole, we did quite well. So that's why you might want to be interested in prediction markets as a way of doing things. Of course, we're going to get to BayesNets. We are just about to publish, it's been accepted in final revisions, a really complicated paper with lots of sums and products and all of that, called Graphical Market Maker for Combinatorial Prediction Markets. Since you all know Bayes nets and can read dependency diagrams, here is the 5-second summary right there. Bayes nets plus prediction markets give you this new alien technology called combo markets. What's going on? Let me tell you the story we tell to the economists. Prediction markets are really good at making forecasts. How does this work? Well, if you want to know whether Obama or Romney are going to win the election, then you put those questions out there onto a market. And if the chance is 50-50, which is equivalent to a price of 50 cents, and you think, no, I think Obama has a bigger chance than that, then you buy shares, which is equivalent to raising the probability. So for all of you economists who like buying shares and selling shares, this is the last I'm going to talk about that, because it's trivially equivalent to raising and lowering the probability. Let the computer do all the transformation under the hood for you. So you have this market on Obama where the probability is, say, 80%, and this market on Romney where the probability is 20%. And as actually happened, someday somebody comes along and buys thousands of shares of Romney, and so the probability goes up to, I don't know, 25-30%. But the probability on Obama didn't change because it's a separate market. This is a problem. There's now a 110% chance that somebody is going to be president. We'd kind of like our markets to obey basic laws of probability. The economists say, no worry, no worry. If you have plenty of forecasters in the market, someone will notice that this is incoherent, and they can do something called arbitrage, which is you raise one and you lower the other, and it's guaranteed free money. So there's a lot of incentive for people who do this sort of thing to do that. And the economist says, aren't markets great? It's like, no, that's not great at all. You shouldn't have to pay people to obey basic laws of probability, like all your chances should sum to 100%. Why isn't your market doing this? Worse than that, sometimes it's not basic laws of probability. Sometimes it's causal relationships in the world. So, not being a political scientist, I don't know which way this might go, but you might have a strong belief that the price of oil depends on who gets elected. So you might say, well, if Obama's elected, then the price of oil will go up. If Romney is elected, the price of oil will go down. Maybe it will go up if both of them are elected by different amounts. That's political science. You might have a physical law that you want to encode this way. And once encoded, you'd like your network to just keep obeying that. You need a way to link these questions together in combination. What if you could represent all the combinations of Obama and Romney winning, or Obama and the price going up or the price going down? That would be a combinatorial market. Problem with combinations is there are lots of them. You get 10 questions, even if they're just true false, you've got 1 million combinations. Your computer can handle that, but your forecasters maybe not. 20 combinations. You get 30 questions, and you've got 1 billion combinations, and now your computer's starting to get slow. Those of you in the Bayes net world should now be thinking about this other bubble up there. Oh, if you have a big probability distribution with lots of combinations, it's intractable to represent brute force. Let's factor it. That's what Bayes nets do. So this was our research question. Can we marry prediction markets and Bayes nets? We know we can let the Bayes net do the probabilities, but can we handle all of that, dirty economic stuff, the buying and selling of trades? Can we make sure that people's assets are tracking in this big combinatorial structure? Answer was yes. A little bit of math, less than we thought we would need, actually showed that, and a whole lot of engineering made it possible. And my co-authors are responsible for most of the progress there. But we're a Bayes net crowd. All of what I just said is equivalent to turn it over. You have a problem with how to get probabilities into your Bayes net. Lots of probabilities from lots of people on possibly lots of questions. How can you do it efficiently? Prediction markets can help solve that problem. They scale very well, and they have a great attention mechanism that lets people hone in on where do I think this is most wrong, where I can see a difference. I don't know anything about the price of oil, but I do think I know the probabilities of who's going to be elected. Let me edit that one. and you're an economist, and you study the price of oil. You say, I don't know anything about the election, but let me go over here to this oil price because I do understand the policies that they're proposing and what I think is going to happen. And the network can put together both of your knowledge without either of you having to learn everything. You said, well, okay, we do that already. You know, what's the big deal? Here's the problem we faced. Elicit and aggregate 130,000 probabilities from 10,000 participants on 1,200 variables over the course of a year and a half. That's 240 probabilities per day, kind of tractable. Some days are a lot heavier than that. Some days are lighter. How can you handle this? Well, could we? Yes. Not all of our results are due to the combinatorial magic. Some we get just by having a market as a good way of aggregating regular forecasts. But on a Breyer error score, where it turns out that, you know, if you average the error over all the kinds of questions we had, you know, 10 answer, 2 answer questions, the error for just tossing a coin or picking uniformly was about 0.5. And if you said, how did the market do as a whole? 0.3. So a substantial improvement, but, you know, maybe not flying colors. We eventually showed that prizes mattered. We offered Amazon gift cards, and if you looked at only those questions where we offered Amazon gift cards for the most accurate forecasts, we were down to 0.1. And I'm really proud of that. Okay, what does this look like when you have all of these things going on? We had forecasts. This was our science and tech market. Again, sponsored by IARP. It was the FOREST program, Forecasting Science and Technology. So we had a great big cluster on, where did it go? Flu trends. I'm not seeing it right now. Change that. We had a pretty big cluster on Bitcoin over here. Another one on space exploration that I hope to look at with a live demo. Top 500 supercomputers turned out to be a string structure where you looked at what's the performance this year, what about the performance next year, 5 years, 10 years, 15 years, 20 years. These are all conditional on each other, and we elicited those conditional dependencies from our forecasters. Not only the probabilities, but also the structure live on the internet. Well, you don't have such a big network, so should you consider this at all? And I think you should at least consider it. It's not absolutely necessary. There's a bunch of wonderful techniques out there that do work pretty well. BKey is one of them. I know IDI, Innovative Decisions Incorporated in my area, has an iterative design approach. I think they call DSEV. I studied with Kevin Korb and Ann Nicholson. Their book recommends a spiral approach to knowledge engineering for Bayes nets. A lot of these are based on some variant of Delphi, and somewhere in there you're faced with, you think the probability should be 0.5 and you think it should be 0.8. How do we pull those two things together? And unfortunately for all of us, Pennock and Wellman in 2005 showed that you really can't do this in general. So what's going on? We really would like to preserve independence. So if forecaster 1 on the left thinks that A1 and A2 are independent of each other, and forecaster 2 also think that A1 and A2 are independent of each other, then we would like our aggregation technique to preserve that independence. But if you just do a linear average, any kind of weight, equal weighting or some sort of optimum weighting, in general, when you average the 4 probabilities out of those 2 binary variables, right, you've got 4 possible states. If you do a linear average of those, then you're going to induce a dependency that nobody thinks is there. This is a bad thing. In general, what happens when you do this on your whole Bayes net is it becomes fully connected, and then you lose all the advantages of a Bayes net computationally, plus it's useful, almost useless for causal inference. Fortunately, if you use a log opinion pool where you're taking the product of the exponentiated weights, you can do a lot better. Right? So for totally independent, that's preserved. For our happy common cause structure, conditionally independent, that's preserved. But alas, using log odds, when you get to colliders, you will induce a dependency across the top. Now, all is not lost. For the rest of you, this is why things have more or less worked okay, because as you can see on the bottom right, you can preserve a weaker kind of independence, which is Markov independence. Those of you who know a little bit about what happens under the hood when you try to do inference on the Bayes net, it turns your beautiful directed graph into an undirected graph, and it has to connect the parents of colliders. So it loses a little bit of independency information, and log odds will preserve that much. But step back a bit. Why is all this stuff impossible? Because there's a bunch of attributes we would like to preserve. Independence is the one that I just told you about. If everyone thinks these things are independent or conditionally independent, we really want the aggregation technique, the sum network, to preserve that. We also want it to obey something called unanimity, which is, if everybody thinks this arc is there, the arc should be there. If everybody thinks the arc is not there, it shouldn't be there. If everyone believes the probabilities are X, the probability should be X. That is not exactly the same as non-dictatorship. Non-dictatorship means you could solve all the rest by just saying, forget it, Charles knows best, so whatever he says goes. Or my algorithm knows best, and it might ignore any or all of you, but what it says goes. Well, in that case, then you don't have the rest of the problems. You just have to submit yourself to the dictator. And the final one that conflicts with other things is proportionality, which means that your likelihood ratios should more or less track with each other. Okay, well, where do markets come in here? Markets are serial dictatorships. When I edit my probabilities, I have the Bayes net's total attention, and I can do whatever I want until I run out of points or money. We can't use real money in the US. So until we run out of points. So I get to do whatever I want. But if I try to move things too far or too fast or too often, I run out of money very quickly, and then the market goes on and the rest of you can ignore me. So I have an incentive to edit strongly where I think I really do know something, and to shut up when I don't. If I come into an area and think, yeah, could be, kind of, maybe it's a little low, I shouldn't be making an adjustment to the Bayes net. Robin Hanson, my colleague, calls this edit out of outrage. If you come along and think, yeah, this part of the Bayes net, it could be a little bit better, move on. There are how many probabilities and variables in this total Bayes net? I don't need you tweaking 95 to 96%. I want you to look over to where you have an expertise and you look and say, what are they thinking? Please make an edit, because that's where you have knowledge. Now, you might be wrong, but that's where you clearly have an edge. You're detecting that this Bayes net is way off where it should be, and the market gives you an incentive to put all of your effort there, because that's where you will get the maximum reward. Okay. I'm going to attempt to actually show you this live, and if not, I'll fall back to the slide. That's not convincing. One, two, three. We'll give this about 30 more seconds and then bail on that attempt and say, Mac display technology. Well, Stefan, can I do a question while I'm waiting for the Mac to decide whether it's going to give me a screen at all?
Absolutely. Who's got a question? We've got a microphone. We just need questions. Anyone? Anyone? Lionel. You've been waiting for this presentation. You were very, very eager to have this presentation. You must have a question. Come on.
What are we trying to do at the end of the day, technically?
Yeah, what we're trying to do at the end of the day is efficiently get probabilities out of your heads into our shared network without going through and asking all of you to go through all the variables, without having to go through an extra process ahead of time to figure out which variables do you think you know about. And, because I don't really care which variables you know about if somebody else just came along and already set them to be pretty good. I want something that makes you as efficient as possible when you're estimating my Bayes net, because I may have thousands of parameters, and I want this thing to be accurate. Oh, and if I'm forecasting, all these probabilities may be changing over time. I want you to be able to update the ones that are affected by recent events. So I can't have a general Delphi process. It's just too cumbersome if my network gets very big. I need to find something that really helps draw the maximum out of the very limited time each of my experts has to give.
With respect to the structure?
So here's how we do the structure. I think we are live now. All right, I've picked Mars. So we're going to look at a question here. Space agencies for the United States, the European Union, and the Russian, yes, have a target to go to Mars. They think they can do this by 2030. Question, when will a human being actually set foot on the surface of Mars? The current estimate there was the year 2030. This all has a Bayes net underneath. So there's 2030. I can adjust that if I think it's a little too pessimistic or optimistic. And that's just changing a probability in the Bayes net. Or I can look at what does it already depend on. And here let's take a quick look at the network. Our graphs are much more primitive than yours. This, in the end, was an academic project, although our ARPA did give us funding to have actual software engineers, which is a good thing. So the question we were looking at here, man on Mars, is directly connected to permanent moon base and human landing on Mars.
But who decided this connection?
In this case, the forecasters decided the connection. We had the different questions up there, and someone along the way said, hey, it should depend on these things. So I'm going to quickly show you, well, okay, it does actually depend. Suppose we get a permanent moon base by 2022. You're going to watch at the bottom, year 2030 changes to year 2026. Somebody says, okay, if we get a moon base by 2022, then we might get to Mars by 2026. And if we don't, then it would be on the higher side of the average. Let's suppose we want to add another. So we search up here for, I think we wanted asteroid. All right, will NASA be able to capture an asteroid and shuttle it into lunar orbit by 2025? So we've added that question. I'm going to assume that it's yes as my answer. And it says, okay, what do you want to adjust this to be? It has temporarily added that link to the network. It's assumed it has zero effect. Now it wants me to change the effect. Oh, and by the way, it said, hey, before you make that, you need to make an edit that's at least this big, because every arc you add is increasing my computational cost. So I want you to make a substantial enough bet. Now in this case, it only had 2 parents. So the network says, this really does nothing to my computational load, just move it 1. So, but I think, if we get asteroid capture, that's a substantial advance. Let's say this would be 2025. I'm using the market interface here, so it's giving me some feedback about points. We have an interface that hides a lot of that for people who don't want to know. I submit the forecast. It says thank you very much. And now if I look at the network, I'm connected to an extra variable. And in this way, we build up the network by people saying, hey, I think this is connected, and I think it's strongly enough to risk this many points in adding that. Back end, how do you get rid of arcs? We made the decision that we know more about getting rid of arcs because we deeply understand the computational limits of our model. So we will periodically run a scavenger that says, there is no weight on this arc and there's been no weight for a few days, whatever heuristic we come up with, we're going to remove that. But we let our forecasters add arcs because we can't possibly have expertise in all areas of the network. Next steps. You may have seen sideways here, evaluating the replicability of social science experiments in Nature and Science. So recent study came out, how replicable are social science experiments? If we do them again with a different pool of subjects, do they reproduce basically the same result? And the answer is, yeah, sort of. The best estimate now, if you combine all 4 of these studies, is about 60% of them replicate. That's better than our initial estimate, but it seems a lot lower than it should be, given a p-value of 0.05. Or, so we thought you wouldn't really think it should be 95% because of Bayes, but we would have thought higher than 60. Well, in addition to doing those studies, these folks worked to do prediction markets, saying, hey, when we do this replication study, will it show the same result? Can you tell by looking at the original paper? And the answer was yes. Prediction markets score along the bottom, so that's probability of replication, 0 on the left, 100 on the right, sorted by market score. Blue means yes, it did replicate, yellow means it did not. In this case, they got super lucky, and there was a clean division that you could have just drawn a threshold and said everything above that probability will replicate and everything below won't. That result in itself wouldn't replicate, right? There's always a little bit of noise. They just got lucky that it was a clean break, that there was nothing above that failed and nothing below that did. But clearly there's signal there. Well, we want to repeat that using a combinatorial market, which is to say, using a Bayes net so the forecasters can say, these studies are related. They used the same method. If this replicates, so will that one. These questions are related within the study. Will it replicate? What's the effect size? What method is the lab using to replicate? We want to figure out, tell us scientists, what does this depend on? Because we want to know what can we trust. And this is hopefully going to be funded by the government. We're waiting in the contracting phase right now for a program, but we're very excited to be able to take this technology and hopefully get not just good predictions, but actual causal knowledge about the dependencies out. And I get to bring Bayes nets into KeyW. So, thank you. Any questions?